All right, hi everyone, my name is Baylen Luke, and for the third time, we're doing the thermal time constant. So after this one, y'all should be experts. And so I was the group reporter, and I'll be discussing, background again, and also my results, and then gonna hit it up with a conclusion at the end. So if you don't know what a thermocouple is, it's two pieces of metal, and it measures it measures a voltage, resistance, and then to a voltage, and then like we did in instrumentation, you can use like a chart, conversion chart, and find out what the temperature is. But to read it, a thermocouple measures the temperature in the form of a potential difference between two dissimilar metals. So what's a thermal time constant? It's a time constant, and a thermal time constant is the rise time characterizing the response to any transient input. So you have like a step function, and you want to figure out what is that slope, and you want to compare it to another one, and you do that by using a time constant, and that's where the significance comes from. And from there, the physical meaning of it is a time constant. It takes the system step response to reach 63.2% of its final value. So it takes 5 time constants for a whole to reach its equilibrium point, but from there, it's 63% of its final value. Lump capacitance method, like everyone else discussed, what it is, it's you're assuming that your temperature is uniform, and from that, all the internal gradients there are no internal gradients, and it's represented by a gradient T equals 0. The temperature is solely a function of time for this method, and also it's everyone must be familiar with this. We learned in instrumentation, we've been encountering this equation all the time with the lump capacitance. And from there, so you keep looking at the equations. This is coming from that lump capacitance method, but it's you're just using the logarithmic part and normalizing the temperatures to get that time. From there, talk about the experiment. Have a nice computer that crashed on us about 5 times for the experiment, and we had to get some help. But after we got it working and I unplugged it, and crashed it, from there, it was simple as taking it, and we had the hot water for our experiment, and you put it inside and make sure you don't touch the sides, because that would alter your results. And then you wait, let it catch equilibrium and let it record all the data and log all the data, and then you use your potato sack gloves and make sure you don't get any steam or anything on your hands, burn yourself, because #1 rule in lab is safety. I'm gonna have to stress that again and waste some more time, because safety is the #1 thing in a lab. You make sure you get long pants, because we don't want any lawsuits or anything. But anyway, let's keep going. So for the first, this is raw data. It's at its ambient. Again, I had the boiling water, so my graphs are going to be inverse pretty much. And you can see it has this little transient response, and then from there we normalized it, and I have a nice curve fit on this. Probably don't have to have one, but this just brings everything dimensionless. So like from 0 to 1, and it makes everything nice. So this is kind of cool. After taking the log of it and plotting it, you can actually see where we took when we took it out of the beaker, we wiped it, and it altered the slope that it was going on. And I thought that was really neat. You can actually see that and visualize. Again, that's whenever, because we were looking at it, we were like, man, well, how much should I wipe it and stuff, because I didn't want to skew the results when I was wiping it. We wiped it with the potato sack gloves too, by the way. And we got a time constant. I'm not sure if the time constant is correct, but If you multiply that by 5, it's kind of within this, it's within this range, this amount of seconds. So from there, for the removal part, a nice long response, and from there you have your nice normalized data that was required, and then at the end you can see like I was talking about the when it each trying to find its equilibrium point, it started oscillating and going all over, and that right there, the log graph represents that. And I have a tau of 0.0153, which I don't believe is correct. It maybe gets some, after class we can talk about it, see what I did wrong. But in conclusion, because in the conclusion, the time constants for insertion versus removal, the big factors that deals with the material properties is that we need the density and the thermal conductivity would alter your stuff, and that's it. And thank y'all for this time.